Dear students, in this video on work, energy and power, we will study spring mass system. It's very important. Now, supposing we have a spring mass system on a frictionless surface. So here we have a spring. One end is connected to this rigid end. The other end is connected to this mass M, and it is lying on a horizontal frictionless surface. Now, this normal length of the spring is called its mean position, and we can take it as origin x is equal to 0. So this is origin x is equal to 0, and now see, by applying this external force, the mass is pushed. So compression of spring is taking place, and displacement from mean position is x here. Now when you compress a spring, this is your daily life experience, that spring will try to push it backwards. और जैसे ही इस फोर्स को हटाएंगे, स्प्रिंग जो है इस मास को पुश करके पहले यहाँ लाएगा, पर यहाँ पे रुकेगा नहीं. It will move ahead of it. See, ये आगे चला जाएगा, और यहाँ भी इसने नहीं रुकना है. It will stop for a moment, and then क्योंकि यहाँ पर एक्सटेंशन हो चुका है, तो अब स्प्रिंग पर इधर की तरफ फोर्स लगेगा. सो मास विल गो बैक टू दिस पोजीशन. सो इन दिस वे ये जो मास है कभी इधर कभी इधर, इट विल कीप ऑसिलेटिंग फ्रॉम हियर टू हियर. इधर जाएगा, स्प्रिंग को कंप्रेस करेगा, वापस आएगा, स्प्रिंग को एक्सटेंड करेगा, फिर वापस जाएगा, स्प्रिंग को कंप्रेस करेगा, एंड इन दिस वे इट विल कीप ऑसिलेटिंग और वाइब्रेटिंग फॉर अ वेरी लॉन्ग टाइम इफ दिस सरफेस इज फ्रिक्शनलेस. नाउ ये जो फोर्स है जो इस मास को हमेशा इस मीन लेंथ की तरफ ले जाता है, दैट फोर्स इज कॉल्ड रेस्टोरिंग फोर्स. यू कैन सी दिस. जब कंप्रेशन है तो रेस्टोरिंग फोर्स इधर की तरफ है, स्प्रिंग खोलने की कोशिश करेगी, और जब एक्सटेंशन है, सी व्हेन इट इज एक्सटेंडेड, मास यहाँ पे आ गया, तब इस फोर्स की डायरेक्शन इधर है. सो रेस्टोरिंग फोर्स इज ऑलवेज डायरेक्टेड टुवर्ड्स द mean position, right? And one more thing, greater is the compression or extension, greater will be restoring force. So it is seen that this restoring force is directly proportional to extension or compression in the spring. So let's see. When a spring is stretched or compressed, a force comes into play which tries to restore the normal length of the spring, and it is called restoring force. And see, the restoring force is given by Hooke's law. So within elastic limits, the restoring force is directly proportional to the displacement from the mean position. Now when I say within elastic limits, that means spring deform नहीं होना चाहिए. स्प्रिंग को आप इतना ज़्यादा स्ट्रेच या कंप्रेस नहीं करें कि वो नॉर्मल लेंथ में ना आ पाए. ओके, एंड सी F is equal to minus kx according to Hooke's law. Now this minus means this force and displacement are in opposite directions, as you have just seen, and this constant k is called spring constant or spring factor. And from here only, this spring constant k is force upon displacement, that is Newton per meter. So SI unit of this spring constant is Newton per meter. And this spring constant is very important. If the spring is hard or stiff, this k is large, and if the spring is soft, then this k is small. Like अगर आपके पास एक स्टील की या आयरन की स्प्रिंग है तो वो हार्ड होगी, और एक कॉपर की स्प्रिंग है तो वो सॉफ्ट होती है कंपैरेटिवली. सो द वैल्यू ऑफ के इज़ मोर फॉर आयरन स्प्रिंग और स्टील स्प्रिंग, एंड इट विल बी लेस फॉर कॉपर स्प्रिंग. एंड से potential energy of a spring. So see here. similar diagram, but let us try to understand it. You see, this is the normal length of the spring, its mean position. Now see, when you push the mass, आपने मास को एक्सटर्नल फोर्स लगा के पुश किया एंड ये डिस्प्लेसमेंट हो गया इसका x, तो इस मास पर एक्सटर्नल वर्क हुआ और इस ये जो एक्सटर्नल वर्क है वो स्प्रिंग में स्टोर हो जाएगा एज इट्स पोटेंशियल एनर्जी. और यहाँ पर सी स्प्रिंग एट दिस पोजिशन द मास इज एट रेस्ट, देयर इज नो मोशन, बट इट हैज़ कैपेबिलिटी ऑफ डूइंग वर्क, सो इट हैज़ पोटेंशियल एनर्जी. और जैसे ही एक्सटर्नल एजेंसी आप हटा देंगे, ये जो मास है दैट विल go back, move back, and it will not stop here, it will cross this position and reach here. So a compressed or stretched spring has potential energy, and you see extension position also, in both the situation it has potential energy. So the work done in stretching or compressing a spring gets stored in it as its potential energy. So we need to find out the work done in compression or extension. So let us assume that for any particular time, say the mass is at this position, so extension is x, and when extension is x, the restoring force F will be along this direction. और इस एक्सटेंशन को थोड़ा सा और अगर बढ़ाना है dx तक, तो हमें एक्सटर्नल फोर्स लगाना पड़ेगा इसी के बराबर kx फोर्स, राइट. सो द वर्क डन विल बी दिस फोर्स इनटू दिस additional displacement. So that's what we are doing it. So restoring force at extension x is F is equal to minus kx. So work done against this force for further extension of dx will be equal to dw, and that is equal to F dot dx. And you can see that the external applied force and dx are along the same direction. So it is F dx, and external applied force in equilibrium will be kx, opposite to this one, into dx. So the total work done for extension from mean position 0 to x will be integration of this one, integration of dw, and integration of this one from 0 to x. And here you can see that constant k can be taken out, and inside integration we have x dx, and this is like x raised to the power n dx. And you know the relation for it. The relation for this is x raised to the power n plus 1 upon n plus 1. So here x is equal to 1. So 1 plus 1, 2, and upon n plus 1, 2. So using that relation, the work done is k x square upon 2. And by definition, this work done is the potential energy stored in the spring. So the potential energy stored in the spring is equal to half kx square. Very, very important relation and very important derivation also. One more important point to note here is, you can see that this potential energy is, this is like equation. If I take potential energy on y-axis, then I can write it as y is equal to kx square. So this is potential energy. So we can say that the potential energy varies as x square, or graph is going to be a parabolic graph. Another important point to note here only is that, let's see, at this position, when compression is maximum, the block comes to stop for a moment and its potential energy is maximum here, and when it reaches at this position, it stops for a moment but extension is maximum. So here also potential energy is maximum. Now at this position its velocity is 0, So kinetic energy is 0. And here also kinetic energy is 0. Okay. Now when you leave it, इस पोजीशन पर इस मास को आप छोड़ देंगे तो ये मास आगे जाएगा, मीन पोजीशन पर पहुंचेगा. Now at mean position its potential energy will become 0. Potential energy हो जाएगी 0 because x is equal to 0. So half kx square is equal to 0. But यहाँ से यहाँ पहुँचने तक इसकी velocity maximum हो जाएगी. So kinetic energy will be maximum. Or we can say that all of potential energy is converted to kinetic energy at the mean position. So यहाँ इसकी velocity maximum हो जाएगी. Now as it moves away, spring का extension होना शुरू हो जाएगा. So velocity will go on decreasing till it reaches the maximum displacement. So in this way ये block जो है यहीं पर oscillation करता रहेगा इस तरीके से. The sum of kinetic energy and potential energy will remain constant. See, kinetic energy plus potential energy will remain constant everywhere, and this is equal to mechanical energy. So the mechanical energy remains constant everywhere, or we can say that the mechanical energy in spring mass system remains conserved when it is moving on a frictionless surface. And let us do its graphical variation now. You see, so we have taken extension or compression on x-axis, energy on y-axis. This is the mean position, and now you see this is the maximum extension, maximum compression, let it be plus minus a, and you see the variation and the sum of potential energy and kinetic energy. So you can see that at mean position the potential energy is 0, at extreme positions potential energy is maximum, and at mean position kinetic energy is maximum, and at extreme positions kinetic energy is 0, right? But the total always remains constant, and that will be equal to half Ka square, right? So total mechanical energy remains conserved. And one more thing I have discussed, that these graphs are parabolic graphs. So the variation of energy is parabolic here. So the plot of potential energy and kinetic energy are parabolic. They are complementary. That is, if one increases, the other one decreases. And the total mechanical energy remains conserved. So we can say that the restoring force in spring system is a conservative force. Now, variation of restoring force with extension in spring. So let us see what happens. Another graph. Variation of restoring force with extension in spring. So F is equal to minus Kx, or F is proportional to x. So we expect the graph to be a straight line. It will be like y is equal to mx, right? And the slope will be negative. See, m is the slope of line, which is negative here, so slope will be negative. And this slope gives the spring constant. See, m is equal to minus k, so the slope of the line gives you the spring constant. And we know that from force extension graph or force displacement graph, the area under graph gives the work done. So the work done in stretching the spring or its potential energy is given by the area under Fx graph. So let us see the graph now. We have discussed the theory part and graph here. See, we have this graph. The slope is negative. You can see minus kx. And if you, this side is extension when x is positive. This side is compression when it is x is negative. And if we choose any point, see, if we want to find out the work done in stretching from mean position to x, then the work done will be given by area of this triangle, or potential energy will be given by area of this triangle OAB. So the work done is given by the area of the triangle OAB. So you should know the graphs and you should be able to solve numerical problems based on graphs. And now let us do a numerical problem based on spring mass system only. But here I have taken a different way of spring. So the extension produced in a spring on hanging a weight of 80 gram is 5 centimeter. Find spring constant, potential energy at this extension. When the weight is allowed to oscillate, what will be its velocity when it passes through the mean position? So here it is not a horizontal spring mass system. Here it is a vertical system where the mass is hanging from a spring. So you can see that this is 80 gram spring and its weight will act vertically downwards. mg will act vertically downwards, right? So it is not on any surface. But when it hangs, the spring experiences some extension. See, if the extension is say x, then the relation first, Hooke's law is applicable here. So applied force is F is equal to 80 gram weight. We convert it to Newton. So convert 80 gram to kilogram, 0.08 kilogram. And we want to convert it to Newton. So multiply by acceleration due to gravity. And let me take it as 10 meter per second square. So the applied force is 0.8 Newton. And according to the question, the extension produced is 5 centimeter or 0.05 meter, and then F is equal to Kx. So spring constant will be F upon X. So 0.8 upon 0.05, it comes out to be 16 Newton per meter. So we have found out the spring constant of the spring, and the next thing is we have to find out the potential energy at this extension. So for that, again we have this relation. Potential energy of the spring is half kx square. So here you can put the values. Half, k is 16, we just found out. X is 0.5 into 0.5 comes out to be 0.02 joule. And so the potential energy at the extreme end is 0.02 joule. And now you see, when the weight is allowed to oscillate, that means वो weight को extend करने के बाद थोड़ा सा extend करके छोड़ दें. So what will be its velocity when it passes through the mean position? So यहाँ पर at mean position, the potential energy becomes 0, kinetic energy is maximum, and we have just discussed that mechanical energy is conserved. So the maximum kinetic energy, that is half mv square, will be equal to maximum potential energy, half kx square, and it is 0.02 joule. And from here we can put the values. You see, v square is equal to, take this 2 to the right hand side, 2 into 0.02 upon mass m, 0.08 kilogram, and simplify it, you get 1 upon 2. So velocity v is under root 1 upon 2, and you can simplify it further. So this is 0.7 meter per second. So when this mass is oscillating up and down, its velocity while passing through mean position is going to be this much. So with this, I come to the end of this video. Thank you for watching it. I hope that it is useful to all of you. Thank you.